Bismillah ar-Rahman ar-Rahim. This is a steel structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University on April 12, 2020. In the last class, we did learn how to find the bending strength for compact shapes, and today, inshallah, we will do the same for non-compact shapes. So here is non-compact shapes, and I taught you how to check if, or the compactness of the cross section to decide if it's whether a compact, a non-compact, or cylinder. As I mentioned previously, most of the standard W, M, S, and C shapes are compact, okay? But few of them are non-compact, okay? That is because of the flange width thickness ratio. What does it mean? If you remember, guys, I told you for these standard shapes, width is always, let's say, compact if Fy is less than or equal 65 ksi. Fy is the yield stress. If the yield stress is less than 65 ksi, it means the web is compact. But if the flange here, in this case, is not compact, is non-compact, let's say, means the whole cross-section will be non-compact, so we need to design it based on non-compactness, let's say, criteria. As I did for the compact beam, the non-compact beam may fail under three limit states. The first one is lateral torsional buckling, okay? This is the first one. The second one, flange lateral torsional buckling, or local buckling, sorry. Local buckling, because flange, it's a part of the cross section, it's a member. So if there is a buckling in this flange, that means it's a local buckling. So it's a flange local buckling. The third one is whip local buckling. Okay, this is flange local buckling, whip local buckling. Okay. And these limit states might happen in the elastic range or inelastic range. Okay, so one more time, guys. This is a stress strain diagram, and let's say this is for a ductile steel. So there is a proportional limit here. If the one of these bucklings happen here, that means it's elastic. If it's happened beyond this point, that means it's inelastic or plastic buckling, okay? And I think you know how to check the compactness for a cross section. Here, this is the width thickness ratio. If it's less than lambda p, which is the compact non-compact limit, and there is a table. I think I showed you that table. So here it's compact, and we will design it based on the last class. Okay. If it's lambda is greater than lambda p, then here it's okay. We can tell equal p less than lambda r or equal lambda r. Here is the limit for cylinder. Okay. So here it's non-compact. Okay. So today we'll teach you how to design the beam based on this, or if it's lies in this category, okay? And here is non-compact, and if lambda is greater than lambda r, and I showed you one example last time, so this is cylinder, and there is, okay, there is a way how to design this one. Here, guys, for the web local buckling, as I just mentioned to you, that the web is all the time, let's say, compact for hot rolled shapes in the manual. So that means this one is not applicable for hot rolled sections. يعني هذا ما بنطبق على hot rolled sections اللي هم بالمانيوال, okay, or shapes, let's say. هذا ما بنطبق. فالفلانج it will be non-compact either from this one or this one. يعني ممكن لازم الفلانج أو واحدة من هاي راح تكون هي limit state for the buckling for non-compact sections. We'll show you how to do that, inshallah, in one example. In the case of built-up welded sections, you know what's the built-up. Built-up something you build it by yourself, by plates, welded together, or hot-rolled sections welded to the plates, and two hot-rolled sections welded together or bolted together. So this is a built-up section. And built-up section might be compact, non-compact, it might be cylinder. So this one is not applicable, or it's not conforming with the built-up sections. يعني هي ما تطبق على built-up sections. The built-up sections section we did by ourselves. Okay. So let's move down and show you these. Yeah, here is. It's mentioned that the webs for all hot rolled sections in the manual are compact. So if we do have non-compact flange, they are subjected only for two limit states, which is lateral torsional buckling or flange local buckling. And web it won't be there. So, or web local buckling. And built up welded sections or shapes might be non-compact, compact, non-compact, cylinder webs. So we need to design them based on that. In the last class, we did use these tables to find LP, LR, if you remember, guys, okay? And I just want to mention one thing here. Look at this footnote here, guys, or look at this cross section. This is W14 by 99 F, and F here means, let's see what does it mean here. If you this one here, that means the shape exceeds compact limit for flexure with Fy is less or equal 50 KSI. Means this is non-compact shape. So you will see that here in the table or ZX tables or table 3.2. And we will use this table to get some information. Right now, let me show you the steps or the summary procedure for or how to design or to find the bending strength for non-compact shapes. So this summary is a very nice one. So let's go through this one. And this will work for compact and non-compact shapes. So here, the first step, we need to define if the cross-section is compact or non-compact, okay? And just 1 minute here, guys. As I mentioned previously, this one is going to work for I and C shape sections. I mentioned that previously in the compact section. So first step, we need to check if the cross-section is compact or non-compact here, guys, okay? So this is the first step. Determine whether the shape is compact or non-compact. If the shape is compact, okay, we need to check for lateral torsional buckling as follows. If LB, this is from the last class, guys. هذا من المحاضرة السابقة. بس هون it's one summary. If LB is less than or equal LP, there is no lateral torsional buckling. Nominal moment strength is equal to the plastic strength, which is Fy times Fy times Z, okay, which is plastic cross sections. Just a minute here, let me, and this one here is equal Fz times Z, Fy times Z, okay? And this is the maximum value you can get. Nothing will be more than this. Okay, if you have anything greater than this value, take this value, okay? And this one thing. And here, the first step. The second step here, if LP is less than LB, so here is if LB is greater than LP or less than or equal LR, there is inelastic lateral torsional buckling, okay? If you remember this, guys, this is here unbraced length, and this is the moment. It was like this, then this, like this. Okay, so here this is P, and let's say this is MN, and here we do have lateral torsional buckling for these two let's say range, lateral torsional buckling, but here is inelastic one, here is elastic one. So let's get back here to our case. So if LP or B is greater than LP, less than L or equal LR, so there is inelastic lateral torsional buckling, which is this one here, guys. Okay, and this is the moment equation value we can or moment equation we will use. So, and I think all these parameters are undefined or defined in the last class. This is accounts for non-uniform bending moment. This is plastic moment, yield stress, elastic section modulus, and we do have LP, LP, LR, and all these values are there. The third case, if LB is greater than LR, there is elastic lateral torsional buckling, which is the third range here. So MN is equal F critical times elastic section modulus, and this actually all the time these should be less than plastic section modulus, and we do have the equation how to find F critical. Okay, so here is the equation how to find F critical, which is this one. This is elastic buckling stress. So these steps for compact shapes, that's what we did last class. In our class today, we need to deal with if the shape is non-compact. Okay, so that means the flange is non-compact. The nominal strength will be the smaller of the strengths corresponding to the flange local buckling and lateral torsional buckling. حكيناها هون إنه الويب local buckling is not there, and no, for the hot rolled sections, web is all the time compact if Fy is less than or equal 65, and this is a big let's say category. طيب الآن we will check lateral torsional buckling, flange lateral torsional buckling. We will take the smallest value, yani the least of these. Okay, so here let me grab the whole page. So if for a flange local buckling, how to decide if the flange is non-compact? Here, if lambda is less than lambda p, there is no flange lateral buckling or local buckling. Sorry, this is a flange local buckling. If lambda is greater than lambda p, less than lambda r, the flange is non-compact. Okay. If the flange is non-compact, so we can calculate nominal moment strength like this. It's similar to the one that we had, but here we have lambda, lambda p, lambda r, lambda p. This is for the flange local buckling. For lateral torsional buckling, if LB is less than or equal LP, there is no lateral torsional buckling. Okay, and if LP here less than LB, or let's say LB is greater than LP, less than or equal LR, there is inelastic lateral torsional buckling. Okay, and this is the equation how to calculate this, and nominal strength here should be less than the nominal or the plastic moment. Okay, and the third one here, guys, if the let's say here LB is the unbraced length. Sorry, I keep mixing up LP, LB. LB, which is this one, this is unbraced length. LP is the limit to decide if it is compact or non-compact and so on. So if LB is or greater than LR, there is elastic lateral torsional buckling, and here is the equation, and this is the how to calculate F critical. Yani this will take back to the same one here. This is MN, this is LP, which is unbraced length, this one, and this one. Okay, so here it's MP, here it's inelastic lateral torsional buckling, here is elastic lateral torsional buckling. Okay. Okay, let's take an example and see how we're gonna calculate that. Okay, and one more time, this procedure is gonna work for compact and compact. شباب هذا راح يعتمد يعني أو this procedure for compact shapes, non-compact shapes. Okay, استخدموا نفسه, و this one will be with you in the exam. Okay, guys, let's solve this example to clarify this procedure. Example 5.6, page 212. It's a simply supported beam with a span length of 45 feet, is laterally supported at its ends and is subjected to the following surface loads. So we do have dead load for 100 pound per foot, including the weight of the beam, which is including the self weight. The live load 1,000 pound per foot. If Fy is equal 50 kSi, is wide flange 14 by 90 is adequate section to carry these loads. يعني هل هذا section قادر يحمل هاي اللودز؟ Okay. Based on the procedure that we did just explain, we need to determine or to check the compactness of the cross section. Okay. So here, guys, this one we can get it from the part 1, table 1.1 for this cross section. So this one is 10.2, and I think I showed you how to get it. And we need to make a comparison with lambda p. This is width to thickness ratio for the flange. Actually, look at this for the flange. So this is for the flange to make it clearer. So we need to compare it with this cross section, with this limit, which is 0.38 Young's modulus dividing by yield stress, and yield stress is 50, so it's 9.15. Okay, and this is lambda r. I don't think so. We will be on this point, or so this is going to be 1 Young's modulus dividing by this, so 24. So if you see here, lambda, which is 10.2, this one is greater than lambda p, but less than lambda r. Okay, this is lambda p, lambda r. So the flange here is non-compact. Okay. Do we need to check the width? No. Why? Because this is a wide flange and Fy is less than 65. Okay, so that means here the width is compact. If the width is compact and the flange is non-compact, so the whole shape is non-compact, so we will design this based on the non-compact procedure. Okay. Okay, since the cross-section is non-compact based on this one here, guys. Okay, so right now we need to check flange local buckling, lateral torsional buckling. And after we did that, we need to pick the least value of these two limit states. So let's start with the flange local buckling. For the flange local buckling, we're gonna use this equation because that's what we see in the procedure. Okay, so in this equation, we need to first calculate the plastic here, a plastic moment, which is this value. It's Fy times Zx. Fy is 50, Zx is 157. And how to get that? I showed you last time. It's going to be from the either table 1.1, and this is the best way, or you can get it from Zx tables, table 3.2. Okay, so this one is going to be 7,850 kip inch. If we need to convert that to kip foot, we can divide by 12. So here we still need SX, and SX is going to be, or it's elastic section modulus, and we can get it from the same place here, table 1.1. So here it's 143, and these two ones, we got them from the manual, from the table. Okay, this one from the table, this one we calculated, and same here we did calculate all these values. So look in all these values here in this equation. So you will get, I think all these ones can be getting or can be getted easily. So here it's gonna be 7,650 kip inch dividing by 12. It will be 637.5 kip foot. And look at this, guys. So this value here is supposed to be less than the plastic section model. The plastic moment here. لازم هاي القيمة هي nominal strength هون تكون أقل من البلاستيك moment هون. Okay. Okay, so right now let's do for lateral torsional buckling, LTB. On we did for flange local buckling, here for lateral torsional buckling. So first, we need to check if, which lateral torsional buckling control, elastic, inelastic. So here we need to get LP, LR from the ZX table, which is table 3.2. I did that last time, and I'll show you right now how to do it. There is an equation to get these two values here, LP, LR, but this is going to be too much work. So let's go to the ZX table and show you how we can get LP, LR for W flange, or let's say wide flange 14/90 section. So if you see here, guys, there is F here, superscript. Okay, so the footnote tells that this cross section is non-compact, and that's what we got. It's non-compact because of the flange. So right now we need LP, LR for this cross section. So if we move this way, guys, LP is 15.1 foot, and LR is 42.5 foot, because there is foot, okay? So we got that for, and one more time, here is how to get ZX from this table, which is 157, and we can get it from table 1.1 easily in the same way. So that's what we got from the table 3.2, which is ZX tables, LP 15.1 foot and LR is 42.5 foot. Right now, let's make a comparison. If you remember, the unbraced length, which is 45 foot here. And why is 45? Because it's mentioned that in the proposal statement is a fixed or simply supported beam, supported laterally here at its ends, and the length of this 45 foot. So this one is the unbraced length, okay? And this one is greater than lambda or LR, which is LR here, 42.5 foot. So this one is gonna fail under elastic lateral torsional buckling, okay? So nominal strength here is gonna be, or nominal moment, since we are dealing with the fracture members, it's gonna be F critical times elastic section modulus, and this one's supposed to be less than the plastic moment, which is this value here. لازم هذا يكون أقل منه. So right now we need to calculate F critical, because this one we can get it easily from table 1.1, which is 143 for this cross section. Okay, so let's move down and see how we can calculate F critical using its formula. Okay, guys, So this is the equation how to calculate the elastic buckling stress. And I told you what is CP means, and this is by square Young's modulus dividing by LB, which is unbraced length, dividing by R sub TS square, and this one here is going to be same to one here, under square root 1 plus this much times JC, and this is one, these ones we can get J, we can get it from the manual. See, it's 1A for doubly symmetric I shapes. And this is elastic section modulus, which is 143, and this is each node. We can get it from the manual. So here, guys, from the manual, we can get Y, which is 362 inch for this cross section, and you know it's a 14 by 90. Okay, so here R sub TS, which is the one we're going to use it here, it's 4.11, and there is equations to get all these ones, but it's going to be a bunch of calculations. This is each node, which is 13.3 inch. This is G, and this is warping coefficient, which is 16,000 inch to power 6. Okay. For uniformly loaded, simply supported beam with lateral support at its end, CP or B is equal 1.14. Let me show you from where we can get this value directly like this without doing any calculations. Last time I introduced this table for you, table 3.1, values for C sub B for simply supported beams, and our case is this one, guys, here. Okay, it's a simply supported beam here, and there is no any bracing along the span length. Just we have a bracing here at this end and the other end, and so here it's none because we do have nothing here. So CP is going to be 1.14 without doing any calculations, because there is an equation, and I did introduce this equation to you last class. So we're going to use this value. Let's get back to our example here. So here I think we have all the information we need to do for this equation. So this is going to be CB, which is 1.14, the one I just got. Pi square 29,000 for the Young's modulus dividing by LP, which is 45 feet, times 12 to convert it to inch, dividing by R sub T, which is we got from the manual here, square under square root 1 plus 0.078 times J, which is 4.06, the one we got from the manual here, guys. C is 1, S or elastic section modulus is 143, and each node we got it from the manual here, it's 13.3, and this is LB times converted to the inch, dividing by R sub T square, and we got the elastic buckling stress is 37.2 and KSI because it's a stress. Okay, so right now, okay, we got the F critical times the elastic section modulus here, guys. So this one, which is the one we got calculated here, and this from the manual, and we use it here, so we already have it. So it's going to be 5,320 kip inch, and this one's supposed to be less than the plastic section modulus, which is 850 kip inch, and this is from Fy times Zx. And which one is the smaller right now? So we got for the flange lateral torsional buckling, or flange local buckling, sorry, the nominal strength was 7,650 kip inch, and we just got it for the lateral torsional buckling is this much. So this much is greater or less than this much, اللي هو for the flange, means lateral torsional buckling controls. يعني القيمة الأقل شباب، إحنا بناخذ القيمة الأقل من lateral torsional buckling أو الفلانج local buckling. فهاي القيمة اللي هي 5320 less than 7650. So this one is control. Right now we got the nominal strength or nominal moment. Okay, we can use LRFD method here, just times 0.9 with the smallest value. So this is this much, which is 4,788 inch or kip inch, dividing by 12, you will get it almost 400 kip foot. And this is for the LRFD method. Okay, let's right now check if this is going to be adequate based on LRFD method or not. So we need to check with the maximum moment. So for the, let's say shabab, for the simply supported beam, okay, loaded with the dead load and live load, what is the maximum moment? The maximum moment, you know, it's going to be at the mid, and this moment is equal WL square over 8. So this is the maximum value for a simply supported beam loaded with a distributed load. And here, the distributed load actually is dead load, live load. So we're gonna check the 7 load cases, and this is the one that control. So 1.2 times, here we did just convert the 400 pound per foot to 0.400 kip per foot, just dividing by 12. Okay, so it's going to be 1.2 times this 0.4 plus 1.6 times 1,000 pound per foot, which is 1 kip per foot. So this is the value, which is 2.08 kip per foot. So here is the W we just got from here, and L is 45 foot. Okay, and here is 8. So this is the value for the maximum moment that we can get under these loading conditions. And here شباب حولناها لفوت عشان هون نخليها فوت، ممكن ما تحولها لفوت وهون تحول هاي القيمة لإنش. Okay, so this one guys here is greater than the let's say the moment capacity for the cross section. So this section is not going to work, it's not good. Okay, لأنه اللود أو المومنت هون أكبر من المومنت capacity للcross section, so this one is not gonna work. Let's do the same for ASD method. For ASD method, guys, here, so the allowable stress here, in the textbook they did use the stress, but let me do the same procedure we do have. So the nominal strength dividing by the safety factor, which is the nominal strength we got is or the least one here, it's 5,320 dividing by 1.67, which is 300 or 3,155.6, which is here, it's kip per inch, dividing by 12, you will get it this much, 265 point. This is kip per foot, or kip foot, sorry. Okay, right now let's check the load we do have. So the load, it's going to be dead load plus live load, and dead load is going to be 0.4 here, shabab. This is kip per foot. It's a kip, sorry, here 0.4 plus 1. So this is going to be 1.4 kip per foot. Okay, so the maximum moment is going to be WL square over 8, same. So this one is going to be this much times 45 feet square dividing by 8. So this here, it's 350 54.73 kip foot. Okay, right now compare this one. This is the applied or the maximum stress under the applied load. هذا الستريس او المومنت اللي راح نحصله under the these load conditions اللي هم dead load live load، وهذا الكاباسيتي للكروس section هيك بقدر يحمل. this one is less than this one, so this section is not good. طبعا in this case guys, here what they did here, they used the allowable here, the allowable stress. It's going to be same because at the end all the time shabab, if you remember I told you the bending stress is equal like this. So this is the stress which is from the basic flexure is dividing by elastic section modulus. Okay, so you can to get the stress, the same stress here, you just can divide it by elastic section modulus, but you don't need to do that. Why you need to do that? Since there is an easier way to calculate or to solve this question. So thank you guys for your watching, and please if you have any question send me an email or chat with me on Microsoft Teams. Sorry to make for this long lecture because I need to finish this topic at one class. Thank you.